magnetic and electrical properties, and this is lecture number 20. So, as you know, in the last lecture we have discussed about electrical properties of material. In fact, we told a lot of interesting things about electrical properties of material. Some of these we will recap, but as these concepts are new and these may not be taught to you. What I mean to say is that all of you may not be exposed to these concepts. So, therefore, it is important for you to know these concepts well from the textbooks. And textbooks means what? Textbooks means obviously textbooks on magnetism, textbooks on electrical properties, but what you will find that those textbooks are pretty big and it is not possible for you to learn in a semester all of these. So, best is to follow things which I am teaching, and then if you do not understand, go back to the textbook and study only those aspects which are required. By the way, so electrical conductivity is very important because electrical properties are used extensively in material science by the nanomaterials. But two important aspects of electrical conductivity. One is the quantum confinement effects I taught you, and this is mainly because of the electronic energy confinement or electronic state confinement, and that means the energy bands will be replaced by the discrete energy states in the nanoscale. That is something which is important in all properties almost, like electrical, magnetic, thermal, optical and also acoustic properties of nanomaterials. Second important thing is the electrical effect, which is nothing but the mean B path of the inelastically scattered electrons become comparable to the size of the system. That means what? If the size of the grains are comparable with the mean path of the inelastic scattering electrons or holes, then they will not get scattered too much, and then you have an increase of conductivity as a result of that. First of all, the first one is more important than the second one. First of all, quantum confinement effects are nothing but change of electronic properties when the material is sufficiently small size, typically 5 nanometer or less, and this effect is observed when the size of the nanoparticle is too small to be comparable with the electrons, wavelengths of electrons. Some of you will have questions because wavelengths of electrons will be in picometer level, right? But that depends on the energy of the system, right? Energy of the accelerating energy of the electrons. But nonetheless, size of nanoparticles which are very less, of the order of 1 or 2 or maybe 5 nanometers, that is what happens. So, quantum confinement effects is only observed when particle size is very small. They are of the order of 1 to 2 nanometers. Okay. Some materials may be little bit higher, but it is 1 to 2 nanometers normally. That is why you see the quantum confinement effects. To understand it, I described it the problem of particle in a box. It is a one dimensional calculation of energy and the wave function, and using this Schrodinger equation, and you know that we can consider an electron or a particle basically sitting in a potential well bounded by the two boundaries, which has a very high value of voltage, almost like infinite, and that is what is shown as by this number infinite, you can see, and in between it can stay. If you do a complete calculation, you will find energy is proportional to n square. That means the quantum numbers square. Similarly, wave function will also be a function of n, sin n by x by L. So, therefore, energies are quantized, electron can only take up those energy levels which are allowed by this calculation, and it cannot take any other energy levels. That is why it is called the quantum confinement. Electron energy levels are confined to certain values. Well, that is the case in a potential well. If a potential well of length L, depending on the values of n, you can have different allowable energy levels, like n equal to 1 and 2, 3, 4, 5, right. That is what is important, and this can be extended to further 2D, 3D, okay, depending on the size of the system, depending on the type of system. As I say, it's basically 0-dimensional nanoparticle, you have a 3-dimensional electronic confinement, 2-dimensional nanoparticles, you have a 2D electronic confinement, sorry, 1D electronic confinement, and 1-dimensional nanoparticles will have 2D electronic confinement. Okay. So, anyway, so that is the basically aspects you have to understand. So, one of the dimensions of the nanostructure, L, that is the potential well dimensions, whatever will be the separation between the energy levels, and that is why it leads to spectrum of discrete energies. How does it look like? That is what it looks like. If you plot density of states G E here versus energy for a 3D or a bulk nanomaterials, where all the dimensions are more than 100 nanometers, then it looks like this. It is a continuous energy band spectrum basically. The moment it becomes a sheet like 2D, okay, then you can have a discrete, and in 1D and 0D it basically becomes very, very discrete. Like in 0D you can have only spikes, or basically they are like a delta functions. Well, that dictates, okay, let me go back, that dictates the things happening in the 1D, 0D, 1D, 2D nanomaterials, the electronic conductions, that is the primary thing. Now, whenever talking about such a kind of things, what is important is to consider is the what kind of contacts it will make. For the 3D nanomaterials or maybe 2D, the contacts will be ohmic contacts, right. But for the 0D and 1D, the contacts will be basically the conduction from the contact to the material will be given by electron tunneling, and that is we have discussed in the last lecture. Tunneling in the sense of electron can pass through, basically this is they think of a point. What is the meaning of tunneling? Electron can penetrate potential energy barrier height higher than the kinetic energy of electrons. That is what is used in the electron microscopes. Many other phenomena, tunneling, electron tunneling microscope, scanning tunneling microscope also utilize that. You can tunnel the electrons from a tip to a surface or to outside by this way. So, I have given you examples of how this can be done. I am not going to discuss about it. What I am going to discuss is the phenomenon of electron tunneling can also be used to develop what is known as a field effect transistor, okay, or FET, and they are made from quantum dots, as you know, right. So, in this case 2 electrodes, a source and a drain, something like this. Let me draw it here on the top and show you. Okay. So, suppose you have a lead here, and then you have a QD quantum dots. There another there is a source here. So, you connect it like this way, and finally you put a capacitor here with some gate voltage, right. So, as you see, this is a voltmeter and this is the current I passing through it. Okay. So, as you see here, in this case we have 2 electrodes, a source and a drain, okay, and they are coupled by quantum dot. All right, that is what is shown in this picture. You can clearly see source and a drain coupled by quantum dot, and they are connected to a circuit. Now, in addition, a gate voltage is provided to the quantum dots, correct, to control its resistance and the ultimately current I which is passing to this circuit. Due to the discrete nature of electrical charge, electrons tunnel from the source to the quantum dots and then to the drain. Because of this gate voltage applied to the quantum dots, electron will tunnel from the source to the quantum dots to the lead, or what is known as a drain, right. So, that is what will happen. Electron tunneling will take place between the lead and the drain. So, discrete nature of electrical discharge, electron tunnel from the source to the quantum dots and at the drain, one at a time. So, therefore, the junction which acts as a capacitor junction which is act as a capacitor here, that is what it is. This is the capacitor. You can see that there is a capacitor which is acting as a capacitor. Suppose a raise in voltage which is given by V is equal to E by C when a silk electron is added. Am I correct? And as a result, electrons will tunnel until a discrete voltage is reached. This effect is known as a Coulombic blockade. Am I clear? So, in this way you can actually create a FET, a field effect transistors, by using quantum dots. Well, let us go to the next subject, the topic what I am going to teach, that is the magnetism in nanomaterials. Well, magnetism is very widely known in the literature, and we use a lot of magnets in daily life, in your cars, in your machines like computers, hard disks are magnets, or your mobile phones, or even many household things. Okay. So, therefore, like refrigerator, TV, washing machines, we are using that. So, how nano will help us to boost the magnetic properties of material? That is what is the purpose of discussions. But what I understand is that all of you are not from the similar backgrounds. Therefore, whatever I am going to teach you, the effect of size and nanomaterials may not fully percolate to you, all of you. So, therefore, I decided I should give you small introduction to the subject and then come back on the discussion of nanomaterials and magnetism. Magnetisms observe in different forms actually, right? What? You can have diamagnetic material, paramagnetic material, or ferro or ferri or antiparamagnetic material. So, I have clubbed ferro, ferri and antiparamagnetism in one class, diamagnetism in one class, and then paramagnetism is another class. All the matter in this world are basically diamagnet. What is the meaning of that? Okay. That means all the material in the world is basically diamagnet. By the way, magnetism is universal, it is present in everywhere. It is present in galaxies or cluster of galaxies, very small value, 1 to 3 micro Gauss. Earth magnetic field is also very important. It is strength of 1 Gauss, and it reverses in fact every 10⁵ years actually, 2⁵ years. And then you find, we have already discussed magnetotactic bacteria, where magnetic particles are present in the bacteria to guide them to move from high height to lower height, or from one place to other place in the water. And then you have magnetic nanoparticles which are found in rocks, and then can be always used to determine the earth magnetic field, both strength and the directions. And do you know that many birds actually have cluster of nanoparticles about 2 to 4 nanometers in their beak area, which help them to move, or homing ability, that is to come back to their home, right? Like pigeons, they have that kind of things. So, now magnetism is very important in all class of life, correct? So, as I told, magnetic materials are different types, okay, ferro, dia, para and ferromagnetism. So, therefore, they need to be first discussed. Okay. Diamagnetism is what? This is a property all material has, and in response to any applied magnetic field, and you do not require any atoms or have a net with a net magnetic moments. This is basically very weak negative magnetic effect. You will see magnetic susceptibility is very small here, or 10 to the -5, and hence it is always masked by the presence of stronger effects like ferromagnetism, correct. So, simplified way of understanding this diamagnetic effect is simply based on Lenz's law, and Lenz's law states that change in the magnetic field will induce a current in a loop of electrical conductor, which will tend to oppose the applied magnetic field. As the electron velocity is a function of energy for the electronic states, diamagnetic susceptibility is essentially independent of temperature, and it tends to exclude the lines of force of material. By the way, do you know that any superconductor excludes all the magnetic lines of forces? So, therefore, this is a perfect diamagnet, that we know. There are many gases like hydrogen, nitrogen, and ionic bonded material like sodium chloride, magnesium oxide, or even cobalt bonded material like germanium, silicon, diamond, carbon, they all have diamagnetism, right. And many organic material also show diamagnetic behavior. That is very clear. And Lenz's law tells you, right-handed law, left-handed law, you know that. It tells you what is the effect of applied magnetic field on diamagnetic materials. So, I am not going to discuss about that. Paramagnetism, which is the next class of material, is so stronger than diamagnetic behavior. There are two types of distinct paramagnetism observed. What are they? One is arising when the atom molecule has a net magnetic moment, other one which comes from the band structure like Pauling spin or weak spin paramagnetism. So, if a net magnetic moment do not cancel each other within a molecule or a atom, then you have a paramagnetism present, right, like oxygen. Oxygen has a net paramagnetism moment of 2.85 Bohr magneton per molecule. So, a point to be noted here that even if there are many electrons in atom, most of the moments are cancelled out, and then you have very few Bohr magnetons available. And in the absence of electromagnetic magnetic field, these magnetic moments will point basically randomly, and therefore, magnetization is almost 0. And when the field is applied, then you can have either aligning force of magnetic field or you have disordering tendency of because of temperature. These two will also happen, and therefore, most of the paramagnetic material will not show sufficient strength to be detected. So, you understand that if there is a net magnetic moment within the molecule or an atom, then you have which do not cancel each other, then only you can have paramagnetism present. And a combined effect of these leads to partial elements of magnetic moments, and the susceptibility to paramagnetic material is very small value. I do not know whether you know it or not. For oxygen, this susceptibility is at room temperature. For oxygen, it is basically 1.36 10 to the power minus 6 meter cube per kg. This is a susceptibility value, very small. But this paramagnetic susceptibility is used in our brain for probing the oxygen atoms, okay, by something known as a PET scan, by which you know which part of brain is working, which part is not working, and it will be used. It can be used to detect if there is a defect in the brain for a person which needs to be corrected or not. So, that is about the paramagnetism. So, from dia to para, very clear that there is increase in the strength of the magnetism because of the net magnetic moment present in the molecule, but it is very small, very, very small. So, no point in discussing about that. Well, I will not go back to discussion of the effect of temperature or other things. Temperature will obviously has a strong effect on paramagnetic materials, because the magnetic alignments can be disordered by the thermal energy field. Okay. So, then come ferromagnetism, or so ferromagnetism has different types actually, right. Like you have a ferromagnetic, antiferromagnetic, ferrimagnetism. Ferromagnetism is what? Ferromagnetism means you have a spins which are isolated or rather not coupled, uncoupled spin, and you apply magnetic field, they align in the direction of spin. Then you can get a magnetic moment, net magnetic moment. Antiferromagnetism is what? You have spins which are up and down. When you apply a magnetic field, they align in such a way that up one is cancelled by the down one, and then you have no magnetic moment. That is why it is called antiferromagnetic. And ferrimagnetism is again similar to antiferromagnetism, except the strength of the up and down spins are not same. So, therefore, there is a net magnetic moment. But nonetheless, both these two, antiferromagnetism, paramagnetism or ferrimagnetism, strength will be much lower than the ferromagnetism, right. The two important ways to understand ferromagnetism in metals is that assuming moments are localized to atoms, okay, electronics moments are localized to atoms, And then you can use band structure giving rise to interaction iterant electrons. And first one is conceptually more easier, or you can assume molecular field theory and also Heisenberg's approach. It should be noted here that even in metals, most of the electrons behave as if they are localized and number of iterant electrons could be small, although we assume electrons in metals are delocalized. Now, if Fe has 8 valence electrons which occupy 3d plus 4s states, 5 3d and 3 2 4s and then 6 3d states, out of 8 electrons only 0.95 in the 4s bands are truly free or iterant, remaining 7.05 are occupied or localized. That is correct. Only the outer shell electrons are delocalized. They can move anywhere in a metal like iron, but then d shell electrons are not outer shell electrons. So, they are kind of part of the iron atom. Similarly, nickel as having 3d plus 4s is equal to 10. So, it has 0.6 as the 4s electrons and 9.4 is the 3d electrons. You must be confused at why these fractional numbers are coming. This occupancy is because of the strength of the nucleus by which the atoms electrons are bound. So, therefore, these are the moments of the electrons which are important. Now, what about the bands theory? I already discussed about band aspects. Metals has to be will have bands because of the localized electrons are not localized to each atom, right. Electrons in a metal are actually in a gas like free electron gas. So, electrons are not localized to a particular atom, they can hop around from one place to other place, and the band theory is because of that. Most of the electrons are rather localized, and a free electron do not contribute to ferromagnetic behavior. Okay, that is something which you have to understand very clearly. Free electrons are like that. Then band theory is able to explain many non-integral values of that. Now, if iron, the 3d electrons are not fully localized as we discussed. About 5 to 8% have some iterant characters, and those electrons are mediate the exchange coupling between the localized moments. So, therefore, we can see that the observed magnetic moment per atom in iron is about what? This is the observed magnetic moment per atom in iron is 2.2 Bohr magneton, right. So, therefore, we can write normally this is what is true, and D is up, and the up, and the down is equal to 7.05, and ND up minus ND down is 2.2. So, therefore, we can write down ND up is 4.62 and ND down is basically 2.42. These are the number of electrons in the d orbital which are down spin and up spins. Okay. So, nonetheless, that means 4.62 electrons or basically 4.5 electron spins are up and 2.5 times 5 electrons are down spin, and therefore, these two the net magnetic moment of that, net spin of that will provide the net magnetic moment. Okay. So, that is something which you should understand very well. Okay, now, what is the effect of applied magnetic field? Right. This is the electronic structure and all this stuff. As you know, if I have pass a current to a coil, we can generate a magnetic field. Okay. It depends on the number of turns and the length of each turn. Right. So, the relationship between applied magnetic field and the current is given by this. It is Ni divided by L. Why Ni? N is the number of turns, I is the current, and L is the length of each turn. Okay. Each turn means you can see there are many turns, right. So, this is one turn, correct. It goes and comes back just like this, right. This is one turn. So, you know that then you can calculate what is the applied magnetic field because of this current flow. So, in fact, Faraday, according to Faraday's experiments or law, any current carrying coil will have a associated magnetic field with it. That depends on the number of coils it presents, n, length of each turn, as well as the current passing through. Now, what is the response to a magnetic field? magnetic induction results in a magnetism, right. So, if you put a material inside this coil, the field which is generated because of the current flow will induce magnetic field in the material. This we know very well, right. Induction basically is of that, whether you are using induction oven or using a induction heater or using induction melting unit. This is what happens. If you have a current passing through a coil, heavy current, the frequency is also very large, megahertz or kilohertz, then you can induce magnetic field in the material, which you are putting inside this coil. So, this induced magnetic field will depend on the susceptibility, right. Depending on susceptibility, you can have, there are different kinds of susceptibility. Normally, vacuum has susceptibility of 0, and so therefore, you can plot B versus H. B is the induced field, or magnetic induced, and H is the applied field. And as you see, for vacuum it is 0, and it increases with 45-degree angle. But if this susceptibility is greater than 0, then it increases very steep. Susceptibility is less than 0, it increases very slow. So, this susceptibility measures the material response to the related to the vacuum. Okay. Why do you assume vacuum has a susceptibility 0? Because that is the standard state. So, otherwise you cannot compare. This is the very important thing we should understand. So, now then how do you understand magnetic susceptibility? It is nothing but a measure of response of an electron to magnetic field, right. So, as you know, electrons are moving around nucleus. So, if you apply a magnetic field, electrons will like to align around in the magnetic field, because electrons are rotating, right, in a circuit, and electron rotating means there is a current associated with it. So, therefore, because it is rotating in a loop around the nucleus, because of that there is a big magnetic moment created. That is simple, like this aspect only. Coil, we can imagine same thing like a coil in place of an electron moving around a nucleus. So, if you have a magnetic field, what will happen? There will be effect on the electronic spin or electronic magnetic properties, right. So, therefore, when such thing happens, electrons may align along the applied magnetic field, or electron may spin down or spin up depending on the magnetic field. So, therefore, there is some net magnetic moment, and these are nothing but summation of all the moments of electrons. Based on these things, you can have 3 types of responses possible, right. That is what we said, the 3 types of magnetism. You can have a high response, that is ferromagnetic material like Fe2O3, okay, hematite, magnetite basically, not hematite, magnetite, or nickel ferrite, Fe, NiFe2O3, F4, okay, they are ferromagnetic. You can have ferrites like alpha iron, cobalt nickel, or gadolinium, where the chi value is very high. Okay. So, that is what we always write, B is equal to 1 plus chi multiplied by mu 0 into H. Mu 0 is the permeability in the vacuum, and chi is basically known as the susceptibility. So, for this ferromagnetic material, chi is very high, it can go 10 to the power 6. Then you have a second type of materials like aluminum, chromium, moly, sodium, titanium, zirconium, a very low susceptibility, almost close to vacuum, right. So, small effect of applied magnetic field, it will not change much. By the way, these things are taken from Callister's book on material science, and you can refer to that. This is available on internet, also free of cost. So, and then you have a third category of material is diamagnetic, we have already discussed, right. Aluminum oxide, copper, gold, silicon, silver, zinc, they have negative value of diamagnetic chi, almost like very small negative value of 10 to the power minus 5 or so. So, that means depending on the applied magnetic field, you can differentiate 3 different types of behavior: ferromagnetic, diamagnetic, paramagnetic, right. You can see that. So, that is something which is very easy to do using this equation called B equal to 1 plus chi mu 0 H. H is the applied magnetic field. Applied magnetic field has a lot of effects, like that is why we wanted to bring this discussion in front of you. Now, what actually happens atomistically? Your diamagnetic material, if you have no magnetic field, nothing happens. There is no magnetic moment basically present in the atoms or molecules. The moment you apply magnetic field, magnetic moments will built in, very weak magnetic moments will built in, but then they will oppose the applied magnetic field. That is what happens. Superconductor is basically perfect diamagnetic material. It perfectly opposes the applied magnetic field. Lines of forces will be repelled perfectly by the so therefore, superconducting magnetics. So therefore, diamagnets are like that. They will oppose the applied magnetic lines of forces. Against diamagnetism, compared to diamagnetism, paramagnetism is a little bit different. So paramagnets will have a weak magnetic moments, as we have discussed. They are very weak magnetic, like oxygen. They are very weak magnetic moments, and they are randomly aligned. So when you don't apply in magnetic field, they are not aligned to any particular directions. The moment you apply magnetic field, some of these things will try to align to the magnetic field. That is what happens in PET scan in brain. When doctors want to do a PET scan in a brain, you have to know which part of the brain is basically acting. It's very simple. I am talking to you now. So that means the part of the brain which is responsible for talking will be, we need a lot of energy, and energy comes from the oxygen, right? The blood from the heart, basically they is supplied to the brain. As you know, the huge amount of blood is supplied to the brain, because brain is doing a lot of calculations and a lot of thinking every time. So when you are talking, then some part of the brain is basically functioning more than the other part, and that part requires a lot of energy. Energy is provided by oxygen. And so therefore, if you probe that oxygen, then we can understand which part is responsible. That doctors are very smart, much smarter than us. So they then apply huge magnetic field to align the oxygen atoms, and they can then image them. That is what happens. If you apply magnetic field, these weak magnetic moments of the oxygen atoms will allow them to align, right? But they will not be perfectly aligned to the magnetic field. They will align at an angle or so. So that will be not perfectly alignments, but this will lead to some kind of a increase of the alignments as compared to random in case of absence of any magnetic field. So then you apply, in the case of ferromagnetic materials, even in absence of magnetic field, there will be alignments of these spins, but they will not be perfectly aligned. So the moment you apply magnetic field, they will perfectly align, and because of that you have a net magnetic moment, which is very high. That is what happens in iron, nickel, cobalt, or in nickel ferrite, or in magnetite. That is what is observed. So this is what happens in a atomic scale picture. So you have understood the effect of field, then you have understood now the atomic scale structure of diamagnetic, paramagnetic, ferromagnetic materials. I hope you are getting some idea of that. So let us now focus on ferro and ferromagnetic materials more. So it is very clear, if you apply magnetic field, there is a huge change in the interaction between the spins present in the ferromagnetic material and the applied magnetic field, and this will lead to magnetization. Or this magnetization is measured in terms of magnetic induction. This is something what I discussed about, that if you flow current through a coil, it produces a magnetic field, and then if you put a material inside this coil, this magnetic field will try to induce a magnetic movement. That is what is known as a magnetic induction. So if I plot magnetic induction versus magnetic field, you know that you have already seen this kind of plots. This will lead to alignments of the domains. Now we are talking from atoms to domains. Domains may have many atoms. So because of a magnetic field, this application of magnetic field, applied magnetic field, these domains will try to align to the magnetic field, and then this domain alignment may grow slowly as you increase the magnetic field. So what I mean to say is that when you have zero magnetic field, so although in each case spin is aligned, but they are in a net scale, they are not aligned to the properly, so that it can give net magnetic moment. You can see these arrows are different directions. So they may cancel out completely, or they will reduce the magnetic moment, right? So now you start applying magnetic field, you see they will be trying to align properly. So as you can clearly see that some of these two fields have aligned more easily, more strongly than these the bottom ones, and then slowly if you increase it, the strength of the alignment of these two things increases, and finally I can see the bottom two has joined together the domains, and at a very high magnetic field all the domains actually are aligned to the magnetic field directions, and finally it gets saturated. That is what happens when you plot B versus X. Now you can actually, all of you know this is H, this is B, so this is exactly happens, right? So, I think I should draw it better way, so that you understand this picture. This is you have studied in your school level books. Okay. So, let me just draw it in a better way, in a different color. Right. So, it gets saturated. Then you reverse the magnetic field, what will happen? This will go like this. You know, this is what is a BH loop looks like. So, you have gone like that, then gone like this, then come back. So, H was positive in this direction, negative in this direction. B is positive in the top, negative in this. Okay. This is something can be correlated with the domain formation, domain walls, domain formation, alignment of the domains. So, I will not go into very big details of these, just to tell you that the concept of single molecule to a domain is very important. So, in a permanent magnet, what are things happens? Okay. So, if you, this is what this initial magnetization state, and then it causes alignments completely, then you remove the H alignments, you started reversing, right, you started reducing that. You can see you have gone up to this magnetic field, this value, then slowly you are reducing. Okay. So, as you reduce, when you make it 0, the net magnetic moment or induced magnetic moment does not go to 0, it has certain value, and that is okay, that remains there. That is the feature of magnetic, permanent magnetic materials, right. And you know, still if you keep on going down or decrease the magnetic field further, you will see that at a value close to exactly, you know, negative value, there will be some negative H is needed to demagnetize the material. The material will not go to completely demagnetized state unless and until you apply negative value of H. Okay, this is negative value of H, minus H you are applying, then only you can make the B 0, correct. So, this is what is known as a coercivity, right. So, coercivity is what? It is the negative H needed to demagnetize the material, correct. And what is this? This is known as a remnant magnetism, this value. This is known as a remnant in NT, sorry. Remnant magnetic, okay, moment or physical field. So, these are the two very important aspects. What is the first one? First one is that if you first to increase the magnetic field, magnetization happened, reach saturation value, saturated value reach it, then you decrease it, and when you bring it to 0, when H becomes 0, because you are decreasing it, H becomes 0, still you have some remnant magnetic field, magnetic induced magnetism remain in the material, and that is what is known as a remnant or remnants actually. But then you keep on decreasing the magnetic field, go negative, 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 unless until you reach a negative H value, minus H, for which the B becomes 0, that is what is known as a coercivity. So, large coercivity is good for permanent magnets. That means you need to apply that much of negative magnetic field or magnetic applied magnetic field to demagnetize the material. And it not that it adds particles of voids to make the domain walls hard to move. Okay, you can do that. There are many ways to do that. Am I clear? So, based on this curve, we have two types of permanent magnets. One is soft, and one is hard. Okay, soft magnetic moments will have a very small BH loop. This is B and H, right? Very small they loop. Okay, and hard magnetic material will have a very big BH loop, right? Applied magnetic field. As you see, for a hard, the area under the curve is very, very large, because that is what is the energy, net magnetic energy in the material. And for small soft magnetic moments, its area under the curve is very small. Think of a switch, okay, magnetic switch. Every time you switch it on and off, if the energy loss is very large, the energy which is getting lost will come as a function of, as a form of heat energy. So, that will be heating of the materials. And that is what in a transformer core, the magnetic material which is used to basically soft magnets, which is very small surface area, or if you want to use it as a switch in computers actually, 0 on and off, 0 and 1, you need to have a soft magnetic material. Am I clear? So, there the area under the curve will be very small. On the other hand, if you want to use permanent magnet, right, okay, there are many applications where you need a permanent magnet, like in a motor, okay, you need to use a permanent magnet. So, there or in a hard disk actually, it is a permanent magnet, there you need to know have a very high light surface area or bigger pH loop. That is the very important aspect you should very understand very clearly. This is the complete picture of BH curve. Okay, forget about these things what I am showing here. So, as you can clearly see, it increases, reaches saturation value, then you decrease, this BR corresponds to remnant magnetism, and then you go to negative value of H, for which the B goes to 0, that is known as a coercivity, right? This is a coercivity, this is the remnant magnetism. Then you can go to the both negative for both the H and H. As the H becomes more and more negative, this is exactly opposite of this curve. This curve is opposite of that. Okay. So, then you can come back again and then follow this. But this is what is known as a BH loop. So, for a hard magnet, this loop area should be as big as possible, big area. Area I mean to say this whole thing is area under the curve, right. And for a soft magnet, small as possible. Am I clear? So, this is something which you should not forget, correct. So, now before I close this lecture, because as I told, I will not discuss about effect of size on the magnetic material in this lecture. I will come back with a new lecture on that. But let me just tell you, magnetic storage is very important, right. You know that earlier days, maybe your father or grandfather used to use tapes to listen music, okay, on a tape recorder. So, in this tape recorder, tape will have magnetic particles present, and then you can actually record something using that tape, nothing but alignment of these magnetic moments. So, if you apply if you rotate this tape and with a magnets between two magnets, you can get the sound back, right. That is what happens. So, head information stored in a magnetic material is pretty, that's known, something known for a long time. So, information is stored by the magnetization in the materials. So, head can actually apply magnetic field H and align the domains. That means basically magnetize that medium and detect the change in magnetization of the medium. That is what these heads are done. This is the head actually, right. That is why it is reading the things. So, now in a recording media like this, okay, you have a recording head, that is what is called head, and it is basically applying a magnetic field and aligning these domains. And depending on the, so when you speak, you can convert this text, whatever speaking, in terms of magnetic field, alternative magnetic field. That I need not tell you. This is routinely done. Even your speaker is whatever I am speaking, it is also same thing. There is a small magnet which is converting this what I am speaking into a magnet, some kind of a magnet is driving that conversion. So, same thing can be done. Okay, you can have a recording head which can align these magnetic particles in the media depending on the how you are speaking, and then if you again take this recorded media to a player and apply magnetic field, you can listen to music. That is what happens. So, there are two types of media. One is called particulate, needle shaped Fe2O3 plus magnetic moment, plus or minus magnetic moment along the axis, okay, like a floppy disk or a tape, right. And thin films like hard drive or even CD drives, they have this kind of things, cobalt platinum chromium or cobalt chrome tantalum alloy. Again, these concepts comes into picture. And so, therefore, the thickness of the these crystals vary from particulate to a thin film. In particulate, thickness is micron size, they are very big. In thin film, they are nanometric size. Okay, why it is so, we will discuss later. So, there is obviously reason for it, why thin films will have smaller, there will be all grains, nano size grains in the thin film deposited on a substrate, and then you can actually do this kind of aspects. So, as you can see that magnetic materials are widely used in various applications. So, now with these basic informations, I will not talk much today. With these basic informations, what I made to believe is that the basic magnetism is something which you need to understand very well. Okay. Most important magnetic material is ferromagnetic material or ferrimagnetic material. They are used a lot in the real life. So, those aspects you need to read a bit, and the chapter 5 of the Dieter Boller's book talks about some of these basic concepts, and some of the basic concepts are known very well, and then they talks also about the effect of nano size, which is the basic purpose of our discussions in the course. So, with these brief descriptions, I stop here and then come back in the next class about the effect of size on these nanoparticles, on the magnetic properties. Thank you.